Hi, my name is Pavel Macenauer and I'm a software engineer at NXP Semiconductors working in the software R&D group for machine learning. And today I'm going to cover TensorFlow Lite delegates on ARM-based devices. So, first of all, I'm going to talk about how to deploy a TensorFlow Lite model, and afterwards we are going to dive deeper into the delegate mechanism, introduce something called partitioning, talk a little about implementing a custom delegate, how to benchmark it, how to check whether it works correctly, and at the end we are going to dive deeper into two specific ones. One being the AnAPI delegate, and the second one being the newly introduced Armanin delegate in the Armanin framework, and of course with some code samples. So, I guess most of you here are already familiar with the TensorFlow Lite framework or TensorFlow framework. It's a popular machine learning framework developed originally by Google and still mostly by Google, but there is a lot of contributors, one of them being Arm, for example. And TensorFlow Lite is a module within TensorFlow, which is there for inference on Internet of Things devices or embedded devices, mostly those having, for example, Cortex-A cores running Linux. But of course, it might be a lot of different platforms. One feature which I'm not going to cover this session is TensorFlow Micro, which is a pretty newly introduced module for microcontrollers, so even smaller devices, but it might be interesting for some of you to check it out. So first of all, when we deploy a TensorFlow Lite model, we still need to start off with implementing or creating our model. We typically do that on a PC using TensorFlow Python interface. For those who are already familiar, it's a, well, it might be a tricky process, but it's not that hard. You define your layers, you produce a model, afterwards you may load the weights from a file, or you may train it, and there you go. You've got a model. The next step is to take this model and load it into a TensorFlow Lite converter. So TensorFlow Lite converter is a module in TensorFlow which converts the model into the flat buffers format. Again, as I previously mentioned, you may take already created model in the protobuffer format, in the Keras format. You may even feed it with low-level APIs, such as concrete functions. And this then gets converted into flat buffers. There's a couple of options which you may perform during this conversion. One of the most notable ones is quantization. So by default, your model, when it gets converted to the TensorFlow Lite format, it's kept in the 32-bit floating point. Now, some devices they have hardware available which performs much better with integer operations, typically 8-bit. Typically, those are NPUs, or you may also have a GPU which runs a lot faster with 16-bit float operations. So there are actually several options for quantization which are available in the TensorFlow Lite converter. One of them is the 16-bit floating point. Another one is the 8-bit integer. And there is also a new experimental feature which allows you to quantize your model into an 8-bit model with 16-bit activations. So this might be useful in case you need a quantized model with slightly better accuracy. So now, after we serialized our format into our model into the TensorFlow flat buffers format, we may run it using the interpreter. One of the notable parameters which is passed when initializing the interpreter is the experimental delegates parameter. So you may actually feed that one with the TensorFlow Lite Delegate API or class. And there is the API which handles TensorFlow Lite Delegates. And there is also the simple delegate API, which is a wrapper around TensorFlow Lite Delegate. So it basically just simplifies the implementation and handles some of the things, or it handles some of the things that you don't have to. And okay, so after we feed our TensorFlow Lite model, which runs inference already on your device, so there are two options here, how the interpreter can run the model. It can be either using the default TF Lite implementation, using the default kernels, which are heavily optimized for the ARM Neon instruction sets. So if you want to run your model on the CPU on your device, this is probably one of the best options to go with. But typically, your hardware has other options available. That may be a GPU, that may be an NPU, that might be a digital signal processor. So if you want to offload the calculation or the computation to such device, you need to use a delegate here. So now, TensorFlow provides several already existing interfaces or implementations. The first one is the AnAPI delegate, which offloads the execution to something called AnAPI, which is an interface targeted for Android devices. It basically defines types and operations, which it may then execute. One thing to note here is that the NXP IDOTAMIX 8 microprocessors leverage this AnAPI delegate in order to accelerate inference. And typically, what this does is that it delegates the execution of AnAPI defined operations to the underlying driver, which then executes the computation on whatever acceleration device is available. This might be the GPU, or it might also be a specialized NPU in the case of IDOTAMIX 8 M+ microprocessors. So then there is the XNNPACK. XNNPACK is a package of kernels, which is an alternative to the default CPU implementation. It also executes your graph or your model on the CPU, but well, you may benchmark it, see what performs better. And Then, of course, the more interesting part is the implement your own delegate class of delegates. Those are custom delegates which don't live as a part of the TF Lite repository. One of them is the VX or OpenVX delegate, which we plan in 2021 to deploy for our Linux IDOTMX8 images. But then there is also the Armanin delegate, which you may find in the Armanin repository already for 3 months under the delegate folder, and it's kind of lives its own life there. So now, before we run a delegate or run the computation on the delegate, it's good to think about whether we even want to do that, because, well, CPU might be better sometimes. So the obvious advantages are performance and power consumption. So typically a GPU or an NPU will perform a lot better than your CPU, because it's, of course, specialized hardware. It has, in case of a GPU, there is the parallel nature, which computes which is suitable, much more suitable for this kind of computation. NPUs also typically fuse layers. So in case you're, for example, running a convolution operation, afterwards you might have an activation or a pooling layer. Some NPUs, they fuse these together and may run it within a single cycle. In the past, I also ran into a use case where the customer he was using an IDOTMX8 microprocessor with, well, not really with a really low-end GPU. But his use case was that the CPU was already running at 100%, so he wanted to free it up a little. So he actually offloaded the execution to the CPU, where it actually took longer to execute inference, maybe by 50%, but he was able to use the CPU for something else. Now, these are the advantages, but there might also be reasons why you might want to consider not running the delegate, and that's in case of unsupported operations, for example. So when an operation is not supported, TensorFlow Lite keeps the execution on the CPU, and it does so by partitioning the graph prior to execution. So now, when your graph is partitioned a lot, there's typically a lot of memory transfers and additional tensor or memory copies required. So this might create quite an overhead. So in case this happens, and for example, your NPU is not suitable for the model you are executing, this might be, it's typically not the case of classification use cases, but suddenly when you are running audio models or segmentation models and stuff like that, where you have more specialized operations required, and those typically won't be supported by your NPU, then you might not want to use a delegate and just run the model on a CPU. Now, I mentioned delegate partitioning previously. So this happens typically in a use case where some operations are not supported. So here in our example, we have four types of operations. We have convolution, we have concatenation, and we have max pooling and average pooling. So In our case, max pooling and average pooling are not supported by our delegate, but convolution and concatenation is. So prior to running inference, what happens is that TensorFlow Lite clusters the supported operations into a subgraph and then keeps the rest. The rest is executed on the CPU, and then there is the subgraph which gets copied to the delegate, and it's executed there. Now, this might introduce several issues. One of them is that you can imagine that in case, for example, you would have two types of operations. Here is example where we have convolution 2D, which is supported by the delegate, but then we have depth-wise convolution 2D, which is not. So this would lead into partitioning the graph a lot, and we want to refrain from that. So there are two parameters available in the simple delegate interface API. One of them, which is supported by most of the already implemented delegates, is the max delegated partitions. So using that, we may actually limit the number of partitions created. Typically, for example, you would set it to a value like 2 or 3, so that only the biggest chunks would get delegated, but the smaller ones would not, in case you would run into a similar use case like the one shown. Then there is a second option, which is min nodes per partition. That one is actually implemented only in the hexagon DSP or the core ML delegate, but it might be a good option to implement it in your own delegate. And that actually what it does is in case you don't reach the number of max delegated partitions, but still have very small partitions, for example, containing only 1 or 2 operations, then you may set the minimum size and only delegate those big chunks. The reason actually to set these values explicitly is, as I mentioned, the memory transfers, which are typically quite costly between a CPU and a GPU or an NPU. So in order to evaluate your delegate, there are several options. The simplest one, or one of the simplest tools, is the benchmark model application, which is also in the TensorFlow repository, and is basically a simple tool. It runs inference for your model and enables the delegate. And after that, it outputs the number of cycles, it outputs the memory footprint, it outputs inference or the warm-up time. So that the warm-up time, that's use case of the AnAPI delegate and the i.MX 8 NPU, which does some, let's say, prior optimizations to the graph before running inference. So the first inference cycle takes quite a long time. For MobileNet here, it's 6 seconds, but afterwards the inference itself or the individual iterations, they take like 3 microseconds. And also, in case you want to check the correctness of your model, which typically involves if you have an NPU it might improve the performance of running the model by actually computing in lower bit operations. So in case this becomes an issue, you might use the inference diff tool for that, which is also in the TensorFlow repository. Now, deeper into delegates itself. So, as I mentioned, one of the popular delegates is the AnAPI. It is defined by the Android C API interface, which unfortunately limits the operations only to 16-bit floats, 32-bit floats, and then 8-bit integers. So it wouldn't be the delegate of choice in case you would want to run, let's say, the hybrid 16-bit, 8-bit model, or in case you would have a pure 16-bit model. On the other hand, it is designed to accelerate your model for Android devices. So if there is a GPU, NPU, or a DSP available, it might run there. And that's also one of the reasons why it's the delegate of choice on i.MX8 microprocessors currently. To the next delegate. So every Linaro virtual client, there is always a talk which involves Armanin. So Armanin is a inference framework, original developed by Arm, but it was donated to the Linaro AI initiative. And the most notable feature is it takes inputs from all kinds of frameworks, so TensorFlow Lite, ONNX, or Caffe, and it's able to run such model through its engine and run it on all kinds of different backends. Those might be Cortex-A CPUs, it might be a Mali, Arm Mali GPU, it might be ethos and accelerators, or there might be a dedicated backend for the i.MX8 processors. If you want to check this out, so check out mlplatform.org or the Armanin repository. There is much more information which can be found regarding the framework there. And the most important feature there is the Armament Delegate, which was introduced in 3 months ago, but it became much more mature in the latest 21.02 release. See the docs, how to integrate it or install it. But as I mentioned, the most notable feature is that if you are using this delegate, you would be able to execute the execution on, for example, ethos and NPU. Currently, I'm not aware that there would be other option to execute on the ethos accelerator using TensorFlow Lite. Also, you may use the Arm Compute library to execute your graph on the Mali GPU. Of course, there is the GPU delegate, which is able to run OpenCL, and also the default implementation accelerates a lot using Arm Neon. So you would have to benchmark your model if you want to use the delegate for that. But for example, for ethos, you don't have any other option. The delegate lives its own life within the Armanin repository, so it's built. It might be built together when you build the whole Armanin package, or you may also build it completely separately. It uses the CMake build system, so in case you are familiar with that, it's just running a single command and it will produce the libarmanin delegate shared library, which you may then attach to your program. There are two interfaces here. One of them is the Python interface, which I will quickly cover now, and the second one is the C++ one. They look very similar, only it's a matter of different programming language. So here, first of all, you import your Python modules. You import the TF Lite runtime, which is a Python wrapper for TF Lite, and then you go on. You load your delegate. That's basically the most important thing here, which attaches the shared library. You specify the backends, specify several other options, and that's it. Afterwards, you only run the interpreter, where you set the experimental delegates parameter, and then you may allocate tensors, run inference, print out the results, and so on. The C++ API looks very much similar. So again, you specify the backends and create an instance. Afterwards, you feed the interpreter using the modify graph delegate function with the Armament Delegate, and afterwards you do pretty much the same stuff like we did in Python. Okay, so that will be it, and some of the links for those of you who are interested to follow up. So there is, of course, TensorFlow. There is the Armanin 2102 with the TensorFlow Lite delegate. So for that one, the best source of information is the GitHub, Armanin's GitHub. And then for NXP i.MX 8 microprocessors on Code Aurora, NXP releases a modified version or a fork of TensorFlow, and also the NNIMX package, which contains some interesting stuff such as the AnAPI delegate, source codes, or a backend for the Armanin framework. So that's pretty much it, and thank you for listening.